Section 1.5 is on velocity and other rates of change. So we're going to start with a question which is more like from non-calculus mathematics. It says a car is driven along a highway for 3 hours and travels 240 kilometers. What's the average velocity of the car? Well, this shouldn't be too hard. We know that the average velocity is equal to the distance traveled divided by the time elapsed. So let's figure this out. The average velocity is equal to the distance traveled, well that's 240 kilometers, divided by the time elapsed, that's 3 hours, which means we get an answer of 80 kilometers an hour. Well, that was satisfying. We're done. We figured out that the average velocity of the car is 80 kilometers an hour. But here's the thing, we've talked about this before. When this car was moving for those 3 hours, there's no way in real life that it would have been traveling at exactly 80 kilometers an hour for the entire 3 hours. So I'm going to say, but this speed is not constant. It changes. Maybe not from second to second, but at least every now and then it's going to be going slightly different. Maybe it comes to complete stop sometimes. Maybe he's going 120 kilometers an hour. So what we're interested in when we're doing calculus is instantaneous velocity. That's the definite velocity at a particular moment. So let's say after 1 hour and 23 minutes and 42 seconds, how fast exactly was this person going? So if we have a function in terms of like an equation, or if we have a graph, we can figure out those things. We can figure out the instantaneous velocity. So let's take a look at an example here. It says the distance s fallen by a freely falling body is equal to s of t equals 4.9 times t squared, where s is measured in meters and time t is measured in seconds. With this in mind, find the velocity of a bungee jumper 3 seconds after jumping off a bridge. Okay, so first of all, we can't just plug in 3. We're interested in 3 seconds. This says s of t, that's a time. Here's our time. Why can't we do that? Why can't we just go s of 3 equals 4.9 times 3 squared? So that's 9 times 4.9, and if you do that, you get 44.1. Why can't we just do that? Because this is s, this is a distance. And so in other words, think of this, this is a position. This is just where the bungee jumper is. We're interested in what the speed is of the bungee jumper. So this is going to take us back to something we talked about in one of the first classes. What you might want to do to get a sense of this is to take another point so you can get an average velocity, just like we did up here, right, using this formula. So another point you might want to take is like if s is 2 or s is 4, so let's do 4, s is 4. If we figure out that position, we would go 4.9 times 4 squared, so 16 times 4.9, and you get 78.4. So with that in mind, we can figure out an average velocity. I'm actually going to do this a bunch of times. I'm going to set up a table here. We've got the time here, and we've got the average velocity here. Okay, so from 3 to 4, the time from 3 to 4. For the average velocity, we're going to use the same formula, distance traveled divided by time. So maybe I'll even put it in brackets here, distance divided by time. So in this case, here's our two distances. We would subtract those distances to get the total distance traveled, and the total amount of time is 4 minus 3, which is 1. If you do that, you're going to get 34.3 meters per second. But again, we've talked about this before. Maybe you say, whoa, a second's a long time. The speed could have changed a lot. The velocity could have changed a lot in that time. Let's take a smaller amount of time. Let's just go from 3 to 3.1 seconds. I mean, that's a tenth of a second. That's a tiny amount. So now, what you're going to have to do in order to figure that out is to plug 3.1 into this formula right here. In other words, you're going to have 4.9 times 3.1 squared. That'll give you the position after 3.1 seconds. Then you're going to have to subtract the position after 3 seconds, which we already know is 44.1. And then you're going to have to divide by the change in time. And the change in time obviously is 0.1 seconds. If you do that, you're going to get 29.89 meters per second. And we'll do this a couple more times. I hope this feels very familiar to you because this is exactly what we've done before when we were talking about slope of tangent lines. Let's say we're going to do 1/100th of a second. So we're going to go from 3 to 3.01. Well, then you need to plug 3.01 into the formula up here, the S of t formula. You're going to subtract the location after 3 seconds, and the distance in time this time is 0.01. What are we at now? We're at 29.449 meters per second. You can see it's not moving, so it's not changing so much anymore. And let's go one more. Let's go 1/1000th of a second. That's our time interval. So we got to find our location at the time 3.001. We got to subtract our location at time 3, and we're going to divide by our change in time, which is just 0.001 seconds. If you do that, you get 29.4049 meters per second. You can see it's really not changing that much at all. Okay, let's pause there for a second and let's graph what we're talking about. So the graph here is a parabola, right? 4.9 t squared, that's definitely a parabola. Faces up or down? Faces up. Where's the vertex? 0, 0. So I'm going to put a dot at 0, 0. Now, we're talking about time when someone jumps off a bridge with a bungee cord on. So we're not going to look at negative times. We're just going to look in the positive. So the parabola is definitely going to face up. I'm not going to try to nail any of the points, but I'm just going to draw it like this. That's my pretty lousy parabola there. And a key point we've been talking about here is when we're at 3 seconds. So at 3 seconds, let's call the point right there, let's call it point P. And we know what that point is right there. Obviously the x value is 3, and the y value is, well, we figured that out. Up here, we figured out that the y value when we plug 3 is 44.1. So we can put that in here. And we started off with another point, which was way up here at 4. And let's say that's Q right there. And what we've done is we've moved Q closer and closer and closer to P, right? So we've moved this along like this. Let's just stop here. I'm actually going to get rid of the 4. We're not interested in that. What we're interested in is this point right here. And we're going to call that 3 plus h. So when we're trying to find our instantaneous velocity at point P, remember what we've done over and over and over here is we've found the difference in the y values, the difference in the distances, because this is distance on this axis, and then we've divided it by the difference in the x values. And remember, this down here is time. And what we're trying to do is get this amount as small as possible, right? We want this 3 plus h to be as close to 3 as possible. In other words, we want h, because that's what the difference is between 3 and 3 plus h, is just h. We want h to be as small as possible. We want h to approach 0. Right? Okay, so one last thing to put in our table. We're not going to go from 3 to 4 or 3 to 3.01. We're going to go from 3 to 3 plus h. So how would we do that? Well, we would have to put 3 plus h into our formula. So we'd have 4.9 times 3 plus h all squared minus 44.1, because that's the location after 3 seconds. And we're going to divide by the change in time. What's the change in time from 3 to 3 plus h? The change in time is h. By the way, just to complete this here, for point Q, the x value is 3 plus h, which means for the y value, you'd have to plug 3 plus h into this formula right there. So you'd have 4.9 times 3 plus h all squared. Right? And now it works out perfectly with our formula we have here. To get the change in y, you'd have 4.9 times 3 plus h squared minus the y value here, 44.1. And then to get the change in x's, you do 3 plus h minus 3, which just leaves you with h. So whether you do it algebraically or use it with our table here, it's working. So let's keep solving this here. We're going to have to square 3 plus h. So we get 4.9. 3 plus h squared is, well, 3 squared is 9, and then we're going to have 6h, right? Remember, we're doing 3 plus h times another 3 plus h, and then we have h squared. We're going to subtract 44.1 and divide it all by h. So now we're going to do the distributive property. You're going to get 44.1, isn't that lovely? Then you're going to have plus 29.4h plus 4.9h squared minus 44.1 all over h. So we can cancel these out. Okay, with two terms you're left with on the top here, you could factor in an h. So you'd have 29.4 plus 4.9h, and that's all divided by h. Great, we have an h on top and bottom. Those are gone. So this is our answer. But remember, we want our h to be as small as possible. So really, what we're doing here is for the instantaneous velocity at time 3 seconds, what we want to do is we want to take the limit. We want to take the limit of this 29.4 plus 4.9h, and we want to do this as h approaches. How much do we want h to equal? We want h to be as small as possible. As q gets closer and closer to p, we want h to get smaller and smaller and smaller. We want h to approach 0. Well, this is a very easy limit to evaluate, because all you need to do is plug 0 into here. You get 29 plus 4 plus 0. You get 29.4 meters per second. Now, if you compare that answer right there, 29.4, with our answers up here, you see that we were very, very close to it just by taking very small intervals. 1/1000th of a second got us very, very close to the actual answer. But to get the true answer, you need to use limits. So hopefully what we've done here seems very familiar. It's exactly the same as what we've done before. The only thing is we're calling it instantaneous velocity before, whereas before we talked about the slope of tangent lines. It actually turns out if you have a graph that compares distance and time, when you find the slope of the tangent line, you've also found the instantaneous velocity. So I'll just say that here. The velocity at time t equals a is equal to the slope of the tangent line at p. In this case, a was 3. That was the time we were interested in. And what we found by using our limit here, our limit when as h approached 0, we actually found the slope of the tangent line through p. The tangent line that would look something like this. The slope of that green line there would be 29.4, and that's exactly the same as the instantaneous velocity. So to summarize what we figured out here, we found that the velocity at point A, or in terms of A, is equal to the limit of change in distance over change in time as change in time approaches 0. That's what makes it instantaneous. Instantaneous means no change in time. So we want to get as close to that as possible. And this is equal to the limit of the function a plus h minus f of a all divided by h as h approaches 0. This look familiar? It should. It's exactly the same as the difference quotient, the alternate difference quotient, which we learned last day. So you can now see that this difference quotient can be used for two things. It can be used to find the slope of a tangent line. It can also be used to find the instantaneous velocity, if you have a graph that's comparing distance and time, or the instantaneous rate of change, which we'll be talking about in just a second. Alright, here's an example. The displacement in meters of a particle moving in a straight line is given by s equals t squared plus 2t, where t is measured in seconds. Find the velocity of the particle after 3 seconds. So if we're interested in velocity, we can use this formula right up here. Again, just like we did before, we need to figure out what's f of x and what's a. f of x is just your formula that you're working with here. It's t squared. Well, actually it would be f of t, wouldn't it? Because t is our input. So our f, our function, is t squared plus 2t. And our a value, that's the input value we're interested in, which is 3 seconds. So we're going to do this. We're going to do the limit as h approaches 0 of f of, okay, a is 3, so we're going to have f of 3 plus h minus f of 3 all over h. So let's do that. We're going to put 3 plus h into the function, this function right here. So we're going to have the limit as h approaches 0 of 3 plus h all squared plus 2 times 3 plus h. Makes sense what we've done so far? We put 3 plus h in here and 3 plus h in there. Now we need to subtract. What are we going to subtract? We're going to put 3 in here, so you get 3 squared, plus put 3 in here, 2 times 3. All that divided by h. Lots of algebra to do here. Okay, 3 plus h squared is 9 plus 6h plus h squared. Distributive property here, plus 6 plus 2h, minus, you can distributive property that, minus 3 squared is 9, and minus 2 times 3 is 6, so minus 6. I guess I could have combined this first, but it'll still work. All over h. Okay, let's see if there's some things we can cancel out here. We have a 9 and a negative 9. We've got a plus 6 and a minus 6. Okay, I think that's all we can cancel. So we've got 6h plus 2h is 8h plus h squared all over h. Why don't we factor in an h on top? So we still have the limit as h approaches 0 of h, 8 plus h all over h. Oh, h and h, we can cancel those out. So we're finally ready to evaluate the limit here. How do we evaluate the limit? We plug 0 into h. I get 8 plus 0. So our answer is 8. 8 what? 8 meters per second. We found the velocity of the particle. At exactly 3 seconds, the instantaneous velocity at 3 seconds is 8 meters per second. Okay, this was an example of velocity, which is a type of rate of change, but there's lots of other rates of change as well in the world. In chemistry, things like reaction rates, how fast the reaction takes place, right? In biology, the change in population size. Populations get bigger and bigger, they get smaller and smaller. We can take a look at the rate at which those things are happening. In physics, there's change in displacement, which is kind of like what we're doing here. Things move to different locations at different speeds. So in all these cases, all rates of change can be interpreted as slopes of tangents, which means we can write pretty well the same thing over again. We can say the rate of change, and remember, velocity is just an example of a rate of change. Slope is just an example of a rate of change. It's how fast the rise changes in relation to run. So for any rate of change, what we want to do is look for the limit of change in y divided by change of x as change of x approaches 0. That's what makes it instantaneous, by getting as close to 0 as possible, which means it's the limit of f of x2, take away f of x1, all divided by x2 minus x1 as x2 approaches x1, because as x2 approaches x1, the change in x is getting closer and closer to 0. This is really just saying the same thing that what we've said up here, but we're saying it a little bit more generally, so it covers all sorts of different things, not just velocity. So here's our last example. A spherical balloon is being inflated. Spherical, a ball, right? Perfectly round. Find the rate of change of the volume with respect to the radius when the radius is 10 centimeters. So we're talking about the volume of a sphere. So one thing you have to know is, what is the volume of a sphere? And the volume of a sphere is equal to 4/3 pi r cubed. And this is volume in terms of r, right? That's the only unknown in the equation. We know pi, that's a number, that's not an unknown. This is the only unknown. So v of r, if you want, is equal to 4/3 pi r cubed. So if we compare this to the formula we have up there, what we want is we want to know the limit of change in v over change in r as change in r approaches 0. So that'll give us the instantaneous rate of change, which means we want the limit of v of r minus v of 10, that's the one we're actually interested in, all divided by r minus 10, and we want r to approach 10. So like for this first function here, we could have put v of v of 11, let's say 11 seconds, and then we could have gotten even closer and said 10.5, and then 10.1 and 10.01. So we're just going to leave it as r here, and then we're going to try to make r as close to 10 as possible, because that's exactly what we did in this big example we did down here, right? It's the same sort of thing we're doing here. Okay, so let's go ahead and complete this. We have the limit as r approaches 10 of v of r. Well, here's v of r right here. It's 4/3 pi r cubed minus v of 10. So we're going to plug 10 in here. So we have 4/3 pi 10 cubed. And that's all going to be divided by r minus 10. Alright, got a bunch more steps here. We could actually factor out 4/3 pi. Why don't we do that? So we take out 4/3 pi, and what's left is r cubed minus, and this 10 cubed, which is 1,000, all over r minus 10. Now, unfortunately, you're going to have to use a difference of cubes here. I don't really want to go through the whole procedure again. Hopefully you're kind of getting familiar with it. So you're going to have your 4/3 pi. When you factor r cubed minus 1,000, a difference of cubes, your a value is r, your b value is 10, so you're going to end up with r minus 10, and your second bracket's going to be r squared plus 10r plus 100, and that's all divided by r minus 10, so difference of cubes here. Then we can cross out the r minus 10s. And we're finally able to evaluate the limit, because we no longer have a denominator of 0. We've canceled that out. So we're going to have 4/3 pi, then we're going to have r squared, but we can start plugging in this value. So 10 squared plus 10 times, there's that r again, 10 plus 100. So 4/3 pi, 100 plus 100 plus 100, so we get 300. So we have 4/3 pi times 300. Oh, we can simplify here. This becomes a 1, this becomes 100. So we have 4 times 100 is 400 pi. Our final answer here is 400 pi, or if you want that, is a decimal. It's approximately 1,260. Now, what are their units? We're finding the rate of change of the volume. Well, volume's measured in centimeters cubed. So it's 400 pi centimeters cubed per, and it's with respect to radius, and radius is measured in centimeters. So same with this one, centimeters cubed per centimeters. Does that make sense? What that's saying is, I'll just circle the first one, it's more exact. For every centimeter increase in the radius, the volume is increasing 400 pi as much. Okay, so this is a rate of change here. All right, thanks very much.